All right, so let's get started. Today we'll be talking about a long-standing problem or feature interaction problems that have been happening between two legacy subsystems, so CPUset and CPUhotplug, and a newer one, the deadline scheduler. So at first I thought it was a feature interaction problem, but really when I started thinking about it, it's two feature interaction problems. So we'll be talking about them today. We'll be seeing what the problems are. I was able, I think, to find a solution to the first one, but obviously we'll need to have more brains and more people looking at the second one, because I don't think I can do it by myself. Okay, so the first half of the presentation we'll be talking about the first feature interaction problem. The second one we'll be talking about solutions that were set forth for that a couple of weeks, 4 weeks ago on the mailing list. And after that, I'm hoping to have some sort of an open conversation on what we can do to address the remaining issues, and if the ideas that I have can fly or have a chance to fly. So before we start, this is not a talk on how the Linux scheduler work. If you are interested in that, there's plenty of documentation out there on that topic. It's also not a presentation where we see what's happening in the deadline scheduler. If you are interested in that, go a year back in Dublin, ELC. There's two really good presentations that go to the heart of what deadline scheduling is and how they work, or how it works. Those two presentations were really good, and I'm pretty sure that the presentations are posted on the website. So if you are interested in that, by all means, these two presentations were definitely worth the time looking at them. Okay, so the first problem that we're looking at was identified by Steve Rostedt maybe 3 years ago on a mailing list. It's a problem that is 100% reproducible, so we're lucky in that way. We don't have to wait 48 hours. It's also reproducible on all architecture. So whether you're ARM, MIPS, RPC, or Intel, you're guaranteed to hit it. All right, so at first I thought, this might be an interesting problem to look at. And I fooled myself in thinking that it would be easy. Keyword here is fool. So people have started looking into this a while back. So Peter Zylstra, Yuri Lely, and Luca Abeni, they thought about using the run queue online, run queue offline, but that turned to have some shortcomings in it, and basically the efforts died there. So talking to Steve, we thought it would be a good idea to revive the effort, and that's where I came in. Okay, so the problem is that at the core of the deadline scheduling model, we have this concept of resource reservation for CPU. So we have a contract between a task and the scheduler. The task is going to utilize some bandwidth, and the scheduler, the deadline scheduler, pledged to give that much bandwidth to the task. Those metrics are really important because if we don't have them, we may oversell the resources in our system. If we are conservative, we might actually not get the bang for the buck for the capability of the hardware. Okay, so if we go dive in, let's start with an example. This is a CPUhotplug operation on a Dragon board. So we have 4 CPUs. Here I have only one deadline task that has a 610 property, so utilization of 6 units on a period of 10. So the units here are not important. It could be millisecond, microsecond. It really doesn't matter. The end result is the same. We have a 60% utilization of the deadline capability. So 60% of 2 to the 60 is the total utilization that we have there. That utilization is carried in all of the run queue simply because this information is held in the root domain, and the root domain is common to all the run queues. Okay, again, so this is at the beginning of the example. We have our utilization, and everyone's happy. If we do hotplug CPU 3, this is the end result. Okay, we see that we completely lost our deadline metric. This is not good, because right now our task is still running, and if we were to have a request for another task that has 60% bandwidth utilization, then we would be overselling our system. Okay? So we have a problem. This is reproducible 100% of the time, so I was very excited about that part. Now, this was a hot plug operation. The same is true for CPUset. It's just a bit more complex to do this with CPUset, and I decided to save that example for problem number 2 that we will be looking at later in the presentation. Okay, so what is happening? Why is it that we're losing our deadline metrics like this? It's all related to the famous root domain. So root domains pertain to scheduling domain. So all of the CPUs part of the scheduling domain will stash metrics in the root domain, and that's exactly where the deadline scheduling people have decided to keep track of the metrics. I think it's a good idea. At first I thought about maybe revising this and spinning off a new data structure, but really when taking a step back and looking at the constraints, I think that putting deadline information into the root domain is a good idea and should be kept there. It's just a matter of handling operations from CPUhotplug and CPUset. Okay, so why is this happening? It is happening because in both CPUset and CPUhotplug, the first thing that happens when those operations are carried out is that the old root domains are destroyed. Boom, you lose all the information that was there. When you look back, all of that information pertaining to root domain is stale because the scheduling is bound to change. The scheduling domain is bound to change. So there was no point in keeping anything there. Deadline scheduling is the first instance where we actually have a case for keeping or inheriting some of the information that was kept. So as I mentioned, the old root domain is destroyed. All of the run queues are placed into the default root domain. Scheduling domain are recomputed, and off that, new root domains are tagged along. So the new root domains are created, and the memory is zeroed out, which is exactly why we're getting a total bandwidth of 0 here. And after that, the hot plug or the CPUset operations are just over. So it's tricky because both hot plug and CPUset subsystem are using the same mechanism. So the code that deletes the root domain and recomputes the new scheduling domain is common to both of them. The difference is that CPUhotplug will carry the operation asynchronously, whereas CPUset will do it synchronously. If it wasn't the case, it'd be a lot easier to fix this, but it isn't, because the information is available at different times during those operations. Okay, so the obvious solution here is to keep track of all of the deadline tasks in the system, and as soon as we have an operation that destroys the root domain, is to circle through those tasks and recompute the utilization that we have for the task into the root domain, exactly the same way it is done when a task is being promoted to a deadline task. So it's, in theory, it's quite easy, and the solution is also quite easy. It's not very complex to think about that. The problem is, as I mentioned, the operations are done synchronously and asynchronously, depending on which subsystem you're carrying it from. And the second thing is, and that's the trickier part, is that tasks in the system, when they get suspended for whatever reason, they are taken off the run queues. So the tasks are taken off the run queues. Basically, you don't know where they went. They could be on a timer, they could be on a mutex. Okay, so keeping track of those tasks could be difficult. If we're talking about running tasks, all you have to do is look in the run queues and then you can add them. But then your snapshot, your vision of your system would be incomplete. Okay? So thought about that, looked at what other people had done, once again with RQ online, RQ offline, and we would always hit the same condition that there's absolutely no way to keep track of tasks that have been suspended, other than starting to have linked lists that we would circle through. And that became difficult because of locking, and it's really a murky solution. So looking at that, doing a lot of soul searching in the CPUset subsystem, found out that each CPUset that you create will keep a list of the tasks that it is handling. And that is really salvation. Because in the end, what we can do after a hotplug or CPUset operation is you circle through the tasks that are handled by a CPUset. You look for a deadline task. Once you have a deadline task, you get a hit on the run queue, and with the run queue, you access the root domain it pertains to. So all you have to do is add your utilization to the root domain, and voila, case solved. Case solved. The advantage of this is that you're treating sleeping tasks and running tasks exactly the same way. In fact, the algorithm that does that is unaware of the status of a task. So really easy, the code that does this is about 20 lines long. Locking is extensive, but that's about it. Okay? The mechanic that is afforded by the CPUset system to do this is actually quite handy. So I talked to Peter Zylstra about this, Luca Abenio as well, and they were under the impression that this was the right way to tackle it. They were happy with that part of the solution, and they asked me to give them more time to do testing. Obviously, there's a lot of ramifications to push code there, so we want things to work properly. But as a whole, we think that this part, well, I'm fairly confident that this part is the right solution. I tried to find other ways to fix this, and really, this is definitely the easiest one. I think the solution itself, if we remove locking and all of the code that we push around to get this to work, might be less than 500 long. So less than 500 lines. So the solution itself is fairly easy. It's a lot of the code that you have to push in order to get this to work. So the advantage, as I mentioned, is very simple. It's treating tasks, whether they're running or sleeping, exactly the same way. And it works with any kind of CPUset topology that you can basically come up with in the wildest dream. Okay, so it's very easy in that way. A bit of a disadvantage is the time that it takes to recompute things. But if you don't want to cope with that, your next solution is to simply prevent a hotplug or CPUset operation in the presence of deadline tasks, and I don't think that's realistic. The thing that really doesn't fix is feature interaction problem number 2, which is what we're going to start looking at right now. Okay, so when we're dealing with CPUset, it has nothing to do with CPUhotplug, this one. So it's strictly related to CPUset. When dealing with CPUset, the problem is that we end up with tasks that are spanning more than one root domain. All right? At first, you can think like, oh, on earth is this possible? In fact, it's quite easy. Okay? For example, we're going back to a system that has just booted, and we're going to look at what's happening on the root domain level, CPUset, and task level. So we have a random task. Pick any one. It doesn't matter. Okay? Again, we're on the Dragon board, so 4 CPUs. So at boot time, we're going to have all of our run queues point to the same root domain. Right? That's on the bottom over there, bottom left. Our task, CPU mask, or CPU allowed mask, really important. So the task is allowed to roam on all 4 CPUs, and on the CPUset side, every task that you spin off on the system by default will end up in the default CPUset. Okay, so everything is great. This is running exactly as expected. So let's get going. We're going to create 2 CPU sets. Nothing has changed, and you can create as many CPU sets as you want. As long as you don't touch the schedule balance flag, nothing will happen. Okay? At this point here, we have the same scheduling domain. All of the CPUs are being handled or being considered for load balancing. There's just more kitchen work here. We have determined that we want CPU 0 and 1 in the first set, CPU 2 and 3 in the second set. But once again, nothing has changed. Nothing has changed because we haven't told the scheduler about this yet. We do so by flipping off the schedule load balance flag. This will trigger the CPUset mechanic, and at the end of that, the scheduler will have a different vision of the world than it had before. What it will have is 2 new scheduling domains. So one scheduling domain for set 1 and one scheduling domain for set 2. And that's where things get tricky. All right, so let's flip our flag. Okay, this is where we're at. And once we flip our flag, the difference is that our root domains are different. We have one root domain for set 1, so RQ0 and RQ1 have a different root domain than RQ3 and RQ2. So this is really important because now we have 2 root domain, but our CPU allowed mask is still set to 4 CPUs. This is exactly what is expected if you're running a CFS task. There's no problem there because there's no accounting done for those tasks. Okay, so even if there's no balancing happening between set 1 and set 2, the scheduler is free to move tasks to those sets in any way it wants. Again, if we're looking at CFS tasks, that's not a problem. But because deadline accounting works based on root domain, and we have metrics that ensures that we don't oversell our system, this becomes a problem. So if we're trying to put our task 1 to a DL task, and we assume that at the moment that we did this, we're on CPU 3, the bandwidth acceptance test will be done on root domain C. It will be accepted, no problem, right? We have our bandwidth, we have enough bandwidth for it. But the task is able to be placed on CPU 0 and 1. But on root domain B here, the deadline metrics have not been accounted for. As such, if we were to add a new 60% task in set 2, the bandwidth test would pass, but we would oversell our bandwidth. So at that point, the whole DL or deadline contract between task and scheduler, they fall apart. And this is the problem I have not been able to solve yet. Okay? And it will take a lot of people to look at this. So I'm offering 3 solutions. The first solution that I have in the patch set is to simply try to foresee all the situations where we will end up with a task that spans multiple root domains. In my opinion, it's a hack. It's brittle because as soon as someone puts or adds a new feature, then we have to make sure that this feature does not introduce this. So we have to introduce guards for that feature so that we don't create tasks in more than one root domain. Okay, so to me, I basically did that to tell people that we have a problem and to at least present an in-between solution while we are thinking about the real deal. Second and obvious is to teach the deadline scheduler how to deal with multiple root domain. Right now, the scheduler, or the deadline scheduler, is able to cope with one root domain. All the mechanic is there. All we have to do is repeat that for as many root domains that the task belongs to. Well, this is interesting. It touches a huge amount of code. We don't know if the mathematics behind the model will still hold with more than one root domain, and it's a locking nightmare. We have to lock all of the domain that the task belongs to while we are doing an acceptance test on all of these root domains. So we might be able to get away with RCU. I don't know why. I don't have all of the details. It might involve some black magic, but I have a little prototype that started doing that. But as I said, it got complex very quickly, and I'm not sure that it has a hope of flying. The third one, which I thought on a plane while flying to a conference, is to basically recompute our scheduling domain before a CPUset operation. That would give us a view into the future as to what the system will look like after. It's always easier to find out tasks that span more than one root domain on current CPU sets rather than waiting afterwards or looking at the input and trying to guess the future. So if we have a snapshot of the future, we can easily pick out which task belongs to more than one root domain, and if we have that, we simply refuse the operation from happening. So this has the advantage of being robust, so any situation can be caught pretty quickly. It moves a lot of code around, there's no doubt about that. All we would have to do is teach the CPUset mechanic how to deal with an input of scheduling domain rather than computing it, 2/3 of the way in the process of rebuilding all of the process of enacting a new set of scheduling domains. So I'm not sure. I haven't looked at all of the ramifications that are possible with this. I'm not sure that is, or I can't say that I'm not sure. I just haven't looked or made a lot of investigation in this. It definitely needs more work, but in my opinion, it's the best of all three scenarios. And that's where you guys come in. This is what I had. As I mentioned, I think more people need to start thinking about this and exchanging ideas on what the best way is to move forward with this. There's a lot of code to change, and I don't think that we can do this iteratively in a patch set, simply because there's just too much work. So I'd rather have a consensus before I start, and then exchange on how that consensus has been implemented. So if you have ideas, I'm more than happy to exchange with you. If you have any questions on what was presented here, I know there's a fair amount of material simply because it touches 3 subsystems, but that's just a reality I've been dealing with for the last 6 months. So now it's really it's entirely up to you. If you have any questions or if you have any suggestions, I'll be happy to listen to them. I know I'm the only one separating you from the beer, but yeah.
Can you go back a few slides, please?
2 slides?
A few slides.
Few slides.
To the point where we had the problem with. Right here. So, if we see the total bandwidth problem here for root domain C, so 629145, whatever the number is.
Yeah.
So, is it overdone for the root domain C right now?
Is it what?
So, is it, have we sold more than what we can do?
Nope, we're at 60%.
Only for root domain C?
Only for root domain C.
It is still fine?
Root domain C is fine.
Okay. But, okay, so I want to understand the problem again. So, what is the problem now?
The problem here is that our task can be roaming between our task can be placed on CPU 0, 1, 2, and 3. Right?
But right now it cannot go away from 2 or 3.
No, it can.
It can?
It
But
can.
We have the scheduled load balance off, right?
Right. Load balancing is off.
Oh, we can still migrate it forcefully.
That's right. And that's the tricky point here. We have to understand that a task can move to all of these CPUs. It's just a load balancing between a set that does not happen.
But it will move forcefully by user intervention now, right? Or
Yes.
This,
Oh no, the scheduler can basically decide that it moved this task to CPU 0.
No, but because scheduled load balance is off.
Load balance is off.
Wake
But,
up path can put anywhere.
yeah. So if the task goes to sleep and then it decides to wake up, the find run queue for that scheduler class can basically decide to put it on CPU 0. There's a whole disconnect on what the CPU is doing, or the CPU operations, or not the CPU, but the scheduling class operations are doing, and the knowledge of CPUsets. So all that's happening here is that there's no load balance between the 2 sets. Nothing more, nothing less. So here, to answer your question, here, we could theoretically have a task that is running on CPU 0, and we could promote it to a deadline task with its utilization of 60%. And that test would pass. But if we have a task running on CPU 0, and then our first task is moved to CPU, for instance, 1, then we don't have enough bandwidth anymore. And yet the system is fooled in accepting that task because we don't have any utilization in root domain B.
Okay, so in this case, because schedule will not do load balance, then the task in the root domain B should have their quota set, and the task in root domain C should have their quota set. But eventually, because they can still move up from the wake up path, as you said, so can't we have something like another root domain over the 2? I know it is not a root domain anymore if we have another root domain over these 2, but can't we have 3 domains here in a hierarchy, and all 3 must have their quota set to, they cannot sell more than it. So, for example, root domain C can still not accept anything more than what it can take. It has this task already. And then there is root domain, say 0 over these 2 domains, and which has to look for the entire system because the task can still move around.
So a virtual root domain.
Kind of.
So it becomes very complex to manage them. That's the problem. Because now this is a very simple topology, but if we have a 24-core system, and we have a hierarchy of them, we can stack them together, right? How many virtual domain do we go up? So if we were able to teach the scheduler to deal, the deadline scheduler, to deal with more than one root domain, in a situation like this, not only the bandwidth acceptance test would be happening on root domain C, but it would also do so on root domain B.
All of them actually.
Huh?
All of them.
Yeah.
PC and the
Yeah.
customer.
So, well, exactly, but this is just a simple example here.
Yeah.
As such, we would have the proper accounting for our whole system. So it basically means that the accounting has to happen on a per CPU basis rather than a root domain basis. But that changes so many things. It basically changes has ramification on the entire deadline scheduler. Anyone else, perhaps? Paulo. Go ahead.
Wasn't the deadline scheduler already reasoning on a per CPU basis? I remember it was partitioned scheduling. It computes the schedule for each CPU in isolation with respect to the other CPU. It's not a global scheduler, as far as I remember. It's
That's
a partition scheduler.
Theoretically, like the base model is uniprocessor.
Yeah.
What they've done here, because the world is SMP nowadays, is they took the uniprocessor model and they multiplied it by the amount of CPUs that we have in a specific root domain. So the mathematics still holds, it's just scaled. But what they've done is they took the CPUs that are found in the root domain of that run queue that the task is currently running on, which is exactly what we have here. So that's why I emphasize on CPU3. CPU3 is associated to run Q3, which points to root domain C. And the deadline metrics are in the root domain. I mean, they've done an outstanding job, right? It's just that when doing that, the ramification of interacting with CPUset was not kept into account, or was not taken into account. Which I can understand. They had enough trouble to deal with to start. Anyone else?
I have a question.
Alex.
I have a question about the data. How was this problem will cause? Like how long latency will this problem will make?
Okay, so to recompute the scheduling domain?
Like you say, data schedule we cannot meet the requirement. So, how better the situation is, how long the maximum latency it will cause.
Again, we need to, because right now it's not going to cause any latency. The recomputation of the scheduling domain and the bandwidth utilization will cause latency. But once that is done, if you don't have enough bandwidth, you're simply not able to meet your bandwidth contract with your task. And whatever the task was supposed to achieve in its utilization or predicted utilization cannot be happening.
Yes, I understand. But did you do some data measurement to see, like you do a CPUhotplug and how long time it will cost?
A hot plug operation. How do you mean the amount of time a hot plug operation does cost?
Yes.
So, no, I have not. Simply because it grows exponentially with the number of CPUs that you have. Well, not exponentially, but linearly with the number of CPUs that you have. Like a hot plug operation is probably the most traumatic thing you can do to the scheduler. Because everything, all of the tasks have to be parked. And everything that's being done stop. The tasks are being moved around. And then everything starts again.
Yes, I have measured this data. I didn't use the data scheduler. It's a normal RT scheduler, like a round robin. It will cost the 60 milliseconds for task transition, like the CPUhotplug cost. And wasn't had done this testing and do some improvement about the CPUhotplug, but he said the 60 milliseconds is normal.
Yeah, no, I don't think there's any, I don't think it's worth to spend any time improving the cost of a CPU hot plug operation, because it's a hot plug. If you're going to do that, something's happening in your system. It's not like you're doing big little scheduling, right, where you're just switching off a core. You're taking it off.
I fully understand on this, but actually there was a target about this and also the Tom's. They said maybe 5 microseconds. That is they want to achieve, but it simply cannot happen.
Fantastic. I just don't see the reason for doing that. Like a CPU hot plug is not something that is autonomous in the system. It's something that's triggered by the user. And if you're going to do that, something is happening that should probably not be happening in your system.
But in theory, actually, you just need to move up your task to others.
Right. But to do that, the mechanic of the hot plug subsystem itself is very complex. And doing a hot plug operation, you need to use a CPU stopper on all of your CPUs. And that's the highest, scheduling class that you have in the system. So everything gets preempted and is scheduled out.
Sorry, I'm not fully understand about the whole impression about CPU hot plug. But you said unplug a CPU will impact all of the CPU in the system.
All of the CPUs in the system.
All of them should be or will be stopped.
Yes.
I guess that's a problem.
It's a problem. Well, it's a problem. That's just how it works right now. Right? And there are reasons for that.
What's the reason?
We have to move tasks around.
That doesn't make sense. It just stop one CPU while you stop all of them.
So my knowledge of that CPU hot plug processing is before Thomas' New World Order, where he really fixed all of the callbacks. So things may have changed, but go back 4 years ago, that's how it worked.
Okay, thank you.
So coming back to the virtual domain thing, so what part of the scheduler is it which actually decides on task wake-up that which CPU it should go to?
There's a scheduling class operation that does that.
So it is part of the scheduling class, right?
Yes.
So that is part of deadline. So
yes.
Some part of deadline code will actually decide that after wake-up,
yeah,
this task has to go to root
yeah.
domain B or C, right?
Yeah.
So instead of having virtual domains, can't we have an aggregated value of all the root domains somewhere, okay? That is for the entire system. So now whenever we have a new task request, we check for that first, okay? The system can take some load, that's fine. And now we go to the root domains, okay? Which root domain have enough capacity to take that particular new task. And the same thing can happen on wake up also. So for example, root domain B gets some task here, okay? And C, the task in root domain C goes to sleep and it wakes up. At that time, the deadline scheduler will come in and see, okay, I may want to get it to CPU 0 or 1, but I have to check on that root domain first, that if it can accept that task or not.
So locking would be horrible. That's the first thing. Second,
but it will still be sequential. It will not be.
Well, you have to lock all of the root domains that pertain to that operation, because tasks can move around while you're doing that.
Yeah, but
well, that's very
yeah,
expensive.
It will still be sequentially, right? You have to go from one domain to one root domain to the other root domain one by one to check if they can accept the task.
Right, but they all be locked at the same time.
No.
Because tasks can move from one CPU to another, and you will only get an accurate picture of what's happening when you have cleared all of your domain. That's the first thing. The second thing here is that this is just a simple example. We can also have someone can decide to spin off a new task, modify the CPU allowed mask to be 0 and 1, and move it into set 1. So at this point here, the task will only be confined to this set and root domain B. So at this point, the whole idea of making this automatic falls apart. Because then we have bandwidth accounting for, or we have deadline tasks that runs on all of the CPUs, then deadline tasks that run on just a subset of CPUs. So it makes things really complex.
But you can screw the system anyway that way. So you can have a task which is big enough not to be handled by a single CPU, and you can actually take that to a single CPU and fix it there. And it is impossible for that single CPU to have that much compute capacity to run that task.
So when that happens, the acceptance check will fail, and that task is not accepted.
No, but the task is already there. So we are just playing the CPUsets now, and we cannot probably fail the CPUset operation, right?
So keep going.
Sorry.
Keep going.
So suppose we have a big enough task, which was suppose the same task, right? Because
Yeah, that task
on all the
was there.
CPUs and that's it. And after it is running, we created a CPUset for just CPU 0 and completely isolated it.
Yeah.
Kept the task there. Now this CPU actually cannot take care of this task at all because it is over its
Oh, there's a check
capacity.
for that.
There's a check for that.
There's a check for that.
And we can fail.
Yeah,
on that.
yeah. There's a test for that.
Okay, but then why will the same problem be there in what you were explaining earlier?
Okay, what?
So you said that we can have more complex problems because we can create more, so we can actually change the CPU allowed mask now and we will have more problems, right?
Yeah, we can have more than one deadline task on a system for sure.
Yeah, but why wouldn't the aggregated bandwidth thing work there in that case?
It gets very complex.
It
Because then
is
we
very
have
complex,
tasks.
yeah, we can't help with the complexity, but
I understand. Right? It's one option. Oh, so you and then Nicola. Oh, you were just yawning. Okay.
So what happens if you do a CPUhotplug, you remove a CPU, and then you don't have enough bandwidth to cover all your tasks being subscribed?
Right.
Do you fail the CPUhotplug
Yes.
operation?
Yes, that's already part of the solution right now.
Okay.
So there's a check before that happens. So the deadline scheduler people did that.
So you can veto a CPU unplug.
Yes.
Okay, so if I understand the problem correctly, it's just if the CPU unplug succeeds, then you lose your accounting somewhere.
That's right.
That's what you want to fix. Okay.
That's right. That's right. Because even if we have a system that is occupied at 30%, we can remove the CPU. The acceptance test will work.
Okay, now I understand. Probably your slides weren't
Yes.
clear enough to me.
Well, there was an example, and obviously, can't you just look at the example?
I can see your slide from here. Sorry.
That's what I thought. So yes, this problem is just a conversation. Varesh's idea is good. It's worth looking into. It will require input from people, and I want input from people because I want to do it right. Thank you for your time.